Hello, everyone, and welcome to this week's SEDS Online webinar. As always, we'd like to thank our sponsorship from IAS, which allows us to offer all of these resources free of charge. And this includes recorded lectures, learning tools, and even virtual field trips. So take a look at the website and you can view all of the new info that is being posted on a frequent basis. And so for today, we have a lecture by Dr. Anna Joy Drury, who is currently a Marie Curie Research Fellow in the Department of Earth Sciences at the University College London. Anna Joy received her master's from the University College London and her PhD at the Imperial College of Science and Technology and Medicine in the UK. Dr. Drury is a paleoceanographer who previously worked as a postdoc at MADOM, Center for Marine Environmental Sciences at the University of Bremen, Germany, and was an outstanding early career scientist of EGU for the 2020 of the SSP division. Her research spans paleoceanography, stratigraphy, and geochemistry with a focus on understanding Cenozoic climate evolution and dynamics. And today she will be discussing some of the evolutions of the Southeast Atlantic carbonate deposition since the Oligocene from 30 million years ago to the present. And as a reminder, the chat will be closed until nearing the end of the presentation, which then you can post some questions. So we'd like to welcome Dr. Drury, and I'll pass on the mic to you.
Hey, thank you, Kimberly, and yeah, thanks very much for the invitation to give this seminar today. Thanks for joining me. On behalf of my co-authors, I'd like to talk to you today about some of the research that I've been doing with them, looking at climate over the last 34 million years. So this infographic here on the right, left, shows the last 34 million years and highlights that this spans a time period characterized by cool house and then later ice house climate change. Or a climate state. So initially with ice sheets on Antarctica and then later on in the Arctic. Oh, sorry, it's not clicking through. So this last 34 million years essentially spans the evolution from a unipolar to a bipolar world. And in this plot here, we can see a summary figure from our most recent paper, which shows the evolution of the cryosphere, approximated by benthic oxygen isotopes here, and the carbon cycle, approximated by benthic carbon isotopes here. And you can see how these two systems have interacted over the last 34 million years, since we had unipolar conditions around 34 million years, and then bipolar conditions appearing much more recently. Now, the carbon cycle, and especially atmospheric CO2, is an important driver of the cryosphere throughout this period. And it's a key factor in driving the transition from a cool house to an ice house world. But the relationship between these two systems isn't constant, as you can see from the different patterns that we see emerging in the wavelets of the carbon isotopes and the oxygen isotopes. They see very different patterns and different orbital imprints captured by these two data sets in response to semi-constant orbital forcing. So one way of looking at how these two systems have interacted over time is also to look at deep sea carbonate deposition. This is because deep sea carbonate in the ocean is carbonate in general in the ocean is an important regulator of atmospheric CO2, thanks to the role that it plays in buffering atmospheric CO2 variations. And deep sea carbonate deposition itself is controlled by a mix of the productivity in the surface water and the amount of dissolution that happens throughout the water column and at the sea floor. So we have quite a detailed view of Cenozoic carbonate deposition and the calcite compensation depth, which is related in the Pacific Ocean. And it's really nice to see in this paper by Pelike et al. That the CCD really changes with some key transitions that we see throughout the last 66 million years, notably the Eocene-Oligocene transition where Antarctica glaciated, and here the Miocene climatic optimum. So we have a good grasp of what the CCD is doing in the Pacific Ocean, but in the Atlantic Ocean, relatively our understanding is quite poor because we don't really have that many Atlantic records to look at in the first place. So the aim of our project was to remedy this by reconstructing changes in carbonate content at ODP site 1264, which is located here in the Southeast Atlantic on Wallis Ridge. So because we wanted to look both at the long-term evolution and the influence of orbital cycles on carbonate deposition, we decided to use XRF core scanning or X-ray fluorescence core scanning to estimate the carbonate content at site 1264. So XRF is essentially based on incident X-rays hitting the surface of the core and causing inner shell electrons to shift from these inner shells to the outer shells to fill a vacancy. And when they do that, shift from the outer shells to the inner shells, when they drop down, they release release fluorescence, which is then detected and can be processed to reconstruct elemental compositions of the sediment. And here I've given two examples. There's the XRF core scanner in Maren, Bremen here at the back. And I've given two examples of kind of an XRF core scanner's worst scenario with a core that has been sampled to pieces, including even with U channels taken out. So this might be quite a struggle to get good data from compared to our best case scenario, where we have nice smooth core surfaces at which we can get a good contact and good data. Fortunately, 1264 was a little bit more like our best case scenario and not too much like our worst case scenario. So what we did at 1264 was we measured XRF core scanning data, collected XRF core scanning data at the entire site to complement existing data that was published in 2016 in Libren et al. And we, as part of a very large international collaboration with groups from Utrecht, Maren, and Southampton, we collected data in 3 different time intervals. So in 2017, here in pink, this data in green had already been collected in 2011, data from 2013, and then most recently in 2018. And to ensure that all of this data could be compared, because it doesn't give absolute quantitative concentrations, but rather relative intensities, we had to spend some time calibrating all of these different measurement campaigns to the 2018 dataset. And the good news was we see excellent agreement through all of these, through all of this time period, despite it almost being the best part of a decade. Now, this took quite a lot of time, and Diederik Liebrand is the person who scanned some of the earlier sections, and also here he is scanning the last section from 1264. So it's been a mammoth amount of work with a large group of people to get this collected, but the result is really brilliant, as we now have over 300 meters of very high resolution data with which we can understand the chemistry of this location in a way that would be unachievable through direct carbonate measurement alone. So once we had the XRF data, one of the ways through which we could use it is also to double check the validity of the stratigraphy at site 1264. So for those who are not so familiar with IODP policy, very often with paleoceanographic legs, they take parallel holes and then try and combine them in a way that they can make a composite, continuous as possible section that may estimate the true sedimentary sequence in a way that a single core with core gaps can't. And on the ship, they had tried to use magnetic susceptibility and other shipboard properties to construct this splice. And that worked very well for this deeper section here in this younger section. But for this interval in the middle, the magnetic susceptibility was very tricky and it was difficult to correlate. So fortunately, our XRF data was able to highlight cycles in this time period. So here we have the hole A in red and the hole B in blue. And then here we see the two data sets overlapped. And you can see mostly that the correlation is excellent, even though the magnetic susceptibility data is incredibly difficult. But it did highlight some areas where there were some stratigraphic issues. So the nice thing with this XRF data was that we were able to take care of these completely. So here we see the example of this situation where there was an offset, and as I already said, our high resolution XRF data was able to make sure that this offset was taken care of, and we now have a continuous sedimentary sequence. You can be very confident that no cycles are missing, and our data is all present. So one thing you might have seen in the background of the last couple of slides is this core photo here. Now, this was also incredibly helpful for building and verifying the composite splice at site 1264. And this core image is essentially a combined image of the core photos, the line scan images of both holes. I'll briefly share how we accessed and extracted this information. So at the time, ODP was collecting core photo images in two ways. They were doing the traditional core box photo, as well as line scan images. And what we did using software that I was involved in developing called Code for Ocean Drilling Data, we essentially chopped out all of the core sections, both from the core box photos, and then cropped the line scan images and built them into composite core images. And you can see here, this is the same core, so core 16 from hole A. And you can see that, interestingly, the core images from the tabletop were sparkling white, so really, and these represented the true color, but the line scan images had, I suspect due to the choice of aperture, got quite a red hue over them. In the end, we chose to move forward with the line scan images from a spectral analysis point of view and a cyclostratigraphy point of view, because they highlighted the cycles in the core much better than in the perhaps more realistic white core photo. So the nice thing using this COD software was we were able to take the core photos from hole A and hole B and build these together to make a almost completely continuous section of the sedimentary sequence below the seafloor on Wallis Ridge. So we used COD-Home for this, or the COD software for this for IGOR Pro. I'll come back to that at the end, but if you want to know more about this software, then I'd direct you to this URL. So going back to the XRF data, so we had our continuous high resolution record, and then we wanted to try and understand what these trends and cycles meant. So once we used the collected the XRF data, and calibrated it to the 2018 intensities, we used the log calcium over iron ratio shown here compared to the shipboard calcium carbonate data in order to get a calibration and to convert our high resolution XRF data to a high resolution carbonate record. There are a few very small gaps which we filled from site 1264, which Librant et al. 2016 correlated using physical property data. So once we had a high resolution 300-meter data set, we also needed to know what age it was. And we had to be quite flexible with this. In the end, we used 4 different approaches, orbital tuning approaches, as no single strategy could be applied across this entire 300 million year interval. So I will briefly introduce the cycles that we tune to. Now, you may all mostly be aware of these, but just in case, we made sure we tuned to combinations of eccentricity, so essentially how circular Earth's orbit is, which has cycles of around 405, 127 and 96,000 years. Obliquity, which has a periodicity of 41,000 years, and climatic precession, which has periods of 24, 22 and 19,000 years, the amplitude of which is actually modulated by eccentricity. So I'll go through the tuning strategies we applied in sections first initially focusing on the interval between 30 and 8 million years. And here essentially we applied two sort of the same strategy, but in two slightly adapted ways. So for this oldest part, the example shown here, we tuned simply carbonate minima to eccentricity maxima. Now, for the last 10 million years, we adapted this strategy slightly because in these long-term 2.4 eccentricity minima, we found that the 100 kiloyear eccentricity cyclicity that we've been tuning to wasn't strongly enough expressed. So we combined this with obliquity to still gain as good as possible age control for this time period. We didn't apply this strategy for the period older than 10 million years, as the obliquity solution is not as well constrained for that time period. Now, interestingly, for the youngest 8 million years, we found that we weren't able to continue tuning to eccentricity or an eccentricity tilt comparison. We also found that actually the phase relationship between the two changed. Here, we in fact found that that carbonate maxima coincided with eccentricity tilt and some precession maxima rather than minima, which we'd seen in the previous interval. So we applied this carbonate maxima to ETP maxima for the period about 8 till 3.5 million years. And then for the youngest 3.5 million years, we relied on an age model created by Bell et al. By correlating the benthic oxygen isotope data to the LRO4 stack. So here's a summary of the data that we produced and have available at site 1264 or on the new astronomical age model. So at the top, we have the oxygen isotopes available in purple from Bell et al., the youngest part, and Lieberens et al. On the oldest part. As there's no data available yet in the middle, I've plotted the De Vleeschouwer 2017 megasplice, oxygen isotope megasplice. At the bottom, we have mass accumulation rates. And then here in the middle, we have our carbonate content dataset in red. And this lowest part focuses in and provides a spectral wavelet analysis, highlighting the power in different frequencies, but focusing on periodicities under 200,000 years. So we've got short-term eccentricity here at the bottom, obliquity periodicities would show up here, and then precession, would show up here at the top. And what we found when we investigated this spectral analysis in a bit more detail is actually that we have 3 distinctly different orbital imprints on carbonate deposition over the last 30 million years. So between about 13 and 30 million years, we predominantly see eccentricity-driven cyclicity. Between 8 and 14 million years, we see precession-driven with eccentricity modulation. And then for the last 8 million years, up to about 3 million years, where the signal starts to degrade, we see obliquity with some precession-driven. So it's quite interesting to see that these transitions to these different periodicities coincide with quite major changes in both the absolute carbonate content. And so we have having here the lowest carbonate content preceding the switch from eccentricity to precession, and then the highest carbonate content when we switch from precession to obliquity. And it's also interesting to see that these switches coincide with interesting climatic time periods, including the Miocene climatic optimum, the mid-Miocene climate transition, and then the late Miocene cooling. So I'll go through these in a little bit more detail over the next couple of slides. So here I've zoomed in on the 10 to 20 million year interval. Here, first we have sea surface temperatures from the North Atlantic. It's quite far away, but it was the nearest sea surface temperature record available. Have the oxygen megasplice in the middle, and then our carbonate data in red here, followed with the mass accumulation rates and the 2 core photos. And again, our spectra at the bottom. Now, the interesting thing here is that the lowest sedimentation rates, lowest mass accumulation rates, and lowest carbonate data all coincided with prolonged warmth as seen in the sea surface temperature record. And this coincides with a period that is known as the Miocene climatic optimum. So this could indicate that these low carbonate content is a result of dissolution due to high CO2 concentrations in the atmosphere. However, the interesting thing is actually that the dissolution seems to predate what we would normally see as the classic definition of the Miocene climatic optimum, based on this decrease here in oxygen isotopes through to where it switches here. And it's interesting to see that these low carbonate content values actually predate the Miocene climatic optimum by about 1.5 million years. So this might suggest that there's some preconditioning of the MCO going on. The earlier onset of dissolution prior to the MCO is also actually seen in the Pacific, although here it seems to be only by 1 million years. So this is data from Kohan et al. Got carbonate and then benthic oxygen isotopes from 2 locations in the equatorial Pacific. You can see the MCO. I've also marked it by a grey bar. However, the carbonate contents drops off 1 million years beforehand. So this really raises some quite interesting, So this raises some quite interesting queries about whether there was actually prolonged warmth preconditioning climate at this time before we actually see the deglaciation across the MCO. So moving back a little bit younger now, we see here that both there's cooling and then ice growth, as defined by the oxygen isotope records, around the Miocene climate transition, so the mid-Miocene climate transition at about 13.9 million years ago. And if we look at what we see in the carbonate data, this coincides both with increasing carbonate content and also the appearance of very strong precession in our carbonate data. And you can also, I know it's perhaps clearer here in the wavelet, but you can also see it in the data. Here the cycles are quite big, quite long in their periodicity. And here you see there's this, on top of these larger cycles, there's this smaller cycles are superimposed. And these come from precession. So it's quite interesting that this rise of precession coincides with the appearance of ice growth and global cooling across the MMCT. So we interpret that as the precession-driven calcium carbonate deposition could indicate a reorganization of surface and or deep water circulation in this region, either leading to an influx of less corrosive bottom waters, meaning productivity-driven precession cycles preserve better, or perhaps there weren't precession-driven productivity cycles before this time period in the surface ocean, and after the MMCT, we see these coming in. So moving a little bit younger again, I now want to focus in on the last 8 million years here. So this is the time period where we see that obliquity actually becomes the most dominant driver of carbonate deposition at site 1264. So what's going on in this time period? So here we come back to the summary figure from our De Vleesgouw et al. Paper in Nature Communications last year. And what we see here is that, as indicated by this arrow, this is the time period where we see the obliquity switch in site 1264. Now, the next figure is a little bit complicated, so I'll briefly talk you through it. What we see here on the left and on the right are phase diagrams of essentially the phase between the oxygen and carbonate data from various different sites, the colors of which and the sites of which are shown down here. Here are all the phase relationships for the sites from the Atlantic, and on the left we see the sites from the Pacific. And what I've tried to highlight here with these black boxes is that before about 6 million years, both in the Atlantic and in the Pacific, we see that oxygen and carbon isotopes are in phase on eccentricity timescales. And there's a quite radical shift towards them being antiphase in the late Miocene, and displaying antiphase behavior in oxygen, on 100 to 1,000 year timescales. And this is at a very similar time period as we see the rise of obliquity in our carbonate record. So why do we see all these changes? Well, essentially, we propose that actually in this late Miocene time period, we see a growing importance of strong high latitude processes, especially in the Arctic. So both perhaps the earliest signs of bipolar glaciation with evidence of increased ice sheets at this time period, but also less continental carbon storage because of land use changes, both with growth of tundra and taiga environments compared to the warmer time periods before. And we suggest that this switch in sort of high latitude biomes, growth in high latitude biomes, drove this switch between in-phase carbon oxygen isotope behavior to antiphase in the last 6 million years. Now, here I'm only focusing in on the scenario in the last 6 million years, but if you'd like to learn more about what we found for the older part, I'd direct you towards this paper, as we found also some quite interesting eccentricity modulation of the in-phase behavior for the period 35 to 6 million years. So taking this information about strong late Miocene cooling and stronger high latitude processes from about 6-7 million years ago, and knowing that this coincides with this strong obliquity signal, what does this tell us about what's happening at site 1264? So the other aspect I want to highlight is that this obliquity-driven pacing really coincides with the highest carbonate carbonate content that we see at site 1264 across the whole of the last 30 million years, also with the highest mass accumulation rates. And we think this is the expression of a multi-million year biogenic productivity event called the late Miocene biogenic bloom. So the late Miocene biogenic bloom is a globally recognized productivity event, but we don't really understand why we see this event at this time. So it's been recognized in both oligotrophic and upwelling areas and reconstructed both with low resolution records, which I've highlighted where they come from here in gray, and now also with high resolution records from the South Atlantic, where we've generated data in the Eastern Equatorial Pacific. And there's two main hypotheses about why we see the late Miocene biogenic bloom when we do. And one is that there must have been an increased oceanic flux at this time period, or that we might be looking at changes to how the nutrient distribution, the global nutrient distribution in our oceans. So we were hoping that our new Site 1264 data could help us to understand which of these hypotheses may be true. So here we can see at the top, we've got our carbonate data from Site 1264, and additionally with some coarse fraction data, low resolution on a reverse axis there. We then also here have the mass accumulation rates, both from Site 1264 and from this other location where we have high resolution data, which is the Eastern Equatorial Pacific. And here we have carbonate mass accumulation rates from 7 sites, which here are stacked together in this black line, and this black stack of Eastern Equatorial Pacific data. And here I've plotted that together with the blue mass accumulation rates from Site 1264. And it is quite remarkable that both of these show an increase in mass accumulation rates shortly after around 8 million years. And this also coincides with when we see strong obliquity appearing. So the synchronous onset could indicate that we're talking about a global increase to the oceanic nutrient flux, because we see it start at a very, very similar time. Both of these records have very good age models, so we can be quite certain that we're talking about a truly synchronous event here. So where may these increased nutrients come from? Well, one suggestion is that they could come from increased glacial weathering. So we've seen here that we have evidence for increased high latitude processes. And if we look at, in more detail, at the benthic oxygen isotope records, which also respond to changes in ice volume, we can see that this time period has exceptionally well expressed obliquity cycles. And we interpreted this as they have also an antiphase behavior with the carbon isotopes, although I don't show that here, that they this antiphase relationship and strong obliquity indicates strong glacial interglacial activity at this time. So that could be some insight into why we see increased nutrient influx into the ocean. Increased chemical weathering could also act as a mechanism to get a greater amount of nutrients into the ocean. And this is a record from Holborn et al. From the South China Sea, comparing planktic oxygen isotopes and benthic oxygen isotopes. And they suggest that around 7 million years, sort of between 7.5 and 7, they see a shift from the summer monsoon into the intensification of the winter monsoon linked to global cooling. And again, this would be a mechanism through which you could get increased nutrient input into the ocean. The last mechanism that could contribute to this is that in the late Miocene, we see an awful lot of evidence for aridification around the globe. So this could provide a larger dust flux that could be transported to the ocean to again provide greater amounts of nutrients. So that's in terms of there being a very strong global expression of the late Miocene biogenic bloom. But that's not the whole story, because there's also a huge amount of regional variability in this event. So here at the top, I've just taken out the mass accumulation rates from Site 1264 in blue and the Eastern Equatorial Pacific stack in black. And what we can see here is that synchronous onset around 8 million years. But when we look at the end of the late Miocene biogenic bloom, we can see that actually it ends sooner in the black record, so in the Eastern Equatorial Pacific, compared to the blue record in the Southeast Atlantic. So actually we see that there's almost sort of over 1 million year long difference in the ending of the late Miocene biogenic bloom at these two locations. And the evidence of there being a lot of regional variability is sort of highlighted also by these mass accumulation records from Expedition 371 here in the Tasman Sea. And you can see here for the last sort of 8 million years that the mass accumulation rates in this geographically quite small area are really, really variable. So there's still an awful lot of complexity here that we don't, that can't fall under the hypothesis of an increase in global nutrient flux alone. So then we have to start looking at, well, so maybe changes in the way the global nutrient flux is distributed. How about maybe these are a cause for some of this regional variability? So what types of things may be driving these changes in global nutrient distribution? So here I've taken a panel adapted from Herbert et al. 2016. And here we see sea surface temperatures, oxygen carbon isotopes from the deep sea, and then evidence for aridification over the last 12 million years. And what Herbert et al. Showed is actually that the late Miocene is when we see strong cooling, but also quite regionally different cooling. So with a lot more cooling in the higher latitudes, which are these upper records here, compared to the equatorial low latitude records. And what this could would cause is increased meridional gradients, which would have affected our ocean circulation patterns and trade winds and driven different inputs of nutrients into the ocean. Likewise, our benthic carbon isotope records show different, show that there's a change in ocean circulation here. Before the carbon isotope shift at about 8 million years, there's low gradients between the Pacific and the Atlantic, and these increase after this big carbon isotope shift, which has been suggested to be down to changes in deep sea circulation. And again, this would have affected how nutrients were distributed around the globe. And I know I showed this aridity plot in the global, under the global hypothesis. The thing is, there's certainly, on average, a greater global flux of dust from the continents to the ocean. But there's also an awful lot of regional diversity. So perhaps both the fact that there was a lot of regional difference in this aridification of the continent, maybe this could have also led to regional differences in nutrient input for different regions. So to summarize, essentially, our records can show now that there's some new insights to be gained about the late Miocene biogenic bloom. We see that there is a synchronous onset from the Southeast Atlantic to the equatorial Pacific, potentially driven by increased glacial weathering, increased chemical weathering, or increased aeolian dust flux, all driving increased oceanic nutrient flux. But likewise, our records also highlight that there's a lot of regional variability in this biogenic bloom event that is probably potentially down to regional differences in sea surface temperatures, ocean circulation, and continental aridification. So if you'd like to know a bit more about this research, a lot of what I've shown today comes from our paper in Climate of the Past, which was actually recently accepted and currently going through the proofs. So hopefully the final version of this should be available online shortly. And yeah, just to summarize what I've shown you today about the last 30 million years, we see, based on our high resolution carbonate record from the Southeast Atlantic, that we see 3 predominant pacings. We see eccentricity up to 13 million years, taken over by precession after the Miocene, mid-Miocene climate transition, and then followed by obliquity-driven climate or carbonate deposition following late Miocene cooling and increased high-latitude processes in the late Miocene. We also see that potentially the mid-Miocene climate optimum was preconditioned by over 1 million years by deep sea dissolution and increased global warmth. And we discussed the various different global and regional processes that may be driving both the synchronous onset, but yet the regional expression of the late Miocene biogenic bloom. So finally, I just wanted to highlight this COD software that we've been working on, Code for Ocean Drilling Data. So it's a software package that helps you integrate and visualize deep sea ocean drilling data, specifically from the DSDP, ODP, and IDP programs. And it runs in IGOR Pro, which is comparable to MATLAB. It has an awful lot of different capabilities that you can get stuck into for data processing, data editing, allows you to extract these composite core photos and splice them together. You can do site-to-site comparisons and adjust, correlate and adjust one site to another site and place them on the same depth and age scales. And it's designed to be accessible for a wide range of users, irrespective of whether you like coding or not. You can set up your own codes with the scripts we've designed, but if you prefer using cursors, then that functionality is inbuilt as well. So actually 2.1 was recently released for IGOR Pro 7 and 8, and Roy Wilkins has actually put on a whole bunch of videos and quick notes to help you get started with this. So, but yeah, any questions, obviously always very welcome to get in touch, and thank you very much for listening.
Oop, took a second to come back on. Great, thank you, Anna Joy. That was a wonderful presentation. Just letting everyone aware, the chat room is open for questions. And please make sure that you state your name and where you are watching from so that we can properly announce where the questions are coming from. But overall, great presentation. Thank you so much. Definitely something that gives some insight and hopefully more to come.
Definitely still lots, it's only scratching the surface at this site. Oh, hang on, maybe I can get access to, oh, okay, I've got the chat up. Any questions?
Yeah, sounds good. While people are typing in, did you want to go into slightly more detail about the software that you had just mentioned at the end of your?
Yeah, I definitely can. So it's I can go back on for a slide. So essentially, this is it came from originally Roy using it as a stratigraphic correlation tool when he was sailing on a number of IDP expeditions, but we've really tried to expand it so that you can use it as a way to compile different data sets. And as you can see here, it also allows you to plot your data superimposed on the core images so that you can see how your data and the cycles within it relates to the core sedimentary composition itself. We've got functions set up so that you can incorporate biostratigraphy to help yourself, for instance, get either an initial biostratigraphic or biomagnetostratigraphic age model, or then to use that to guide it for tuning or site-to-site correlation. So yeah, we've tried to get it ready for a number of different uses, and also to really make it flexible both for people who are comfortable coding or people who'd rather just use browsers and click and sorry, not browsers, cursors and menus. So it's really, it should be designed to be quite intuitive for different types of users, depending on what you're comfortable with.
Really interesting. And this, it says there it's designed for IGOR Pro. Does that mean that it can be included in it, or is this its own standalone package?
So unfortunately, at the moment, it only runs, we need a framework to run it in. So it runs within IGOR Pro, much like, I guess, people have coding packages set up for MATLAB. So that is the only downside at the moment. IGOR Pro is not free, although they do offer good discounts for academics and especially for students. And they also offer a free trial, so you can sort of have a look and see if you like it. So that's the downside of, but I guess MATLAB's also not free. But it does, you can use the trial version of IGOR Pro even after the 3-day. I think it just has certain restrictions on it, but the software itself, the package we've designed is available here, and you can download that without obviously that's free. If you spot any bugs, please let us know. But it's always more beta testing is always good.
Absolutely. Just checking in if there are any questions in on the chat room. Please make sure that when you're typing your message, you are responding to everyone, so that we can all see the messages, because otherwise, if you only respond to the SEDS Online chat, only the moderator of the SEDS Online can actually see it. So please don't be shy, ask any questions. It was quite an intense presentation, but it was nonetheless one that was very informative. So definitely have some, please don't be shy for asking questions here. And we have a great software package. Yeah.
But yeah, there's still lots to delve into this with. So, I mean, at the end of the day, it's also a good starting point. We now have a solid stratigraphy and age model there. So hopefully this will provide the basis for more in-depth future research, perhaps comparing smaller time periods.
Absolutely. Okay, we have a question from Yiming Liu. can we, I'm sorry if I don't say this correctly, Sun Yat-sen University in China, can we really attribute the weight of calcium carbonate percentages drops from the -97% to -94% to carbonate dissolution, or could it just be like a difference in dilution by non-carbonate particles?
Yeah, so that's a really good question. I didn't show that data in this presentation, but we did look at the other XRF data that we collected. So I'll put my bottle away and fiddle with that. And that's we have potassium and iron, silica, and we basically all of these elements co-varied and didn't show big changes across this time period. So yeah, so there's basically, especially for this Miocene interval here, we didn't really see carbonate is still most of what is there. So there wasn't a massive influx of other material. So we can't completely exclude it, but considering the context of also very high temperatures preceding the MCO, and the fact that also the coarse fraction increases across this interval may indicate that dissolution is a likely factor here, although we can't completely exclude these other factors. But this is we think that it's, I guess, predominantly dissolution rather than greatly increased dilution or winnowing, for instance. So I hope that answers your question.
I think so. I mean, there's so many multiple factors that can play into this, but one could definitely be a major contributor or a major factor more than others. But I guess more testing is needed to figure this out. So hopefully maybe future PhD students.
Yeah. The age model is there and ready to use. So that's at least one less thing to worry about.
Yeah, and so we have another question from Stephen in Wales. Thinking about the depth of the CCD, is there any modeling of how this may evolve in the future?
I can't directly think of, as in for future climate predictions, presumably. I can't directly think of a paper, but I'm sure there are, especially around the Eocene and Oligocene transition. I think there was a big deepening of the CCD. Yeah, great. Thanks for confirming. There was a big deepening of the CCD once ice appeared on Antarctica, and I believe there's been quite a lot of modeling looking at how that relates to the CO2 decrease and ice growth at that time period. So that could be, I think, quite applicable to future scenarios as a means of showing us what might be if we greatly increase our CO2 levels, that it might really push up or get our CCD to be a lot shallower than it is in the present day. Vaguely remember the Palika et al. Paper also looking into that to a certain degree.
That's always good. I mean, there are so many models that are learning from the past to hopefully predict what can be in the future. So that's a lot of what modeling potentially is. So looking forward to potentially what that that means and then what actually happens. We have another question from Kate Giles. Again, I'm sorry if I mispronounce your names, from El Paso, and I think that's from El Paso, Texas, United States, but please correct me if I'm wrong. So she says, great talk, Anna. Can your results bring any insight into the onset of the Messinian salinity crisis?
So I have to, that's not something I've directly considered, but that would be around 6 million years. So it would be interesting to see whether that might, with especially the carbonate content data, whether that may affect some of the dissolution, if because one of the theories is that it reduced the salinity, the Mediterranean outflow water being quite saline, that could have affected global ocean circulation. So I've not considered it before actually, but yeah, that could feasibly, it would be interesting to look at the carbonate content data around that time period to see if we see any sort of signals. Also, when we get carbon isotope data available for that time period to look at the interbasinal gradients in a bit more detail, that could be a really interesting thing to check, because it's close enough that you might expect some signal if there was an effect of that.
Interesting. Definitely something to potentially consider and look into. We have another question from Patrick Hensel from FAU Engerland, Bavaria, Germany. He says, "Thank you for your talk, Anna Joy. My question is there any dependence between the calcium carbonate accumulation and the H2CO3 content of the seawater? Is it possible to figure it out?"
So that's it's not a problem I've worked directly on, but I mean, if your seawater was undersaturated, it would certainly affect how much CaCO3 was where possible to accumulate. I think in terms of I wonder if you could backtrack it. I guess you would need to know more about what the original carbonate rain coming down was, and then we'd know what our content was now. So I suspect you might need to, perhaps by looking at what the composition was of the carbonate that's left, and whether it's evidence with a lot of fragmentation for dissolution and what the primary producers might have been. You might be able to back this out through modeling, but it's it's not something I've looked into myself. But I'd potentially also, if you got more detailed sea surface or temperature records, that I believe plays a role as well in how corrosive your waters are. So that would, I think there's some lower resolution boron calcium records that are a more direct reconstruction of the pH of done at site 1264 and site 1267, I think, in Kenda. I want to say Kenda et al. In 2014. So that could be a good place. Perhaps you could use that as a lower resolution background of understanding how corrosive the deep sea was. There's a means to look at the high frequency changes.
Great. So I actually have a follow-up question to that. And would it matter at that point to get down to the mineralogical level, as far as if it's aragonite or calcite or even low or high mag calcite, based off carbonic acid and dissolution purposes of what can be then kind of modeled backtrack of what originally was?
Yeah. So that's a really, really good consideration. If you did want to look into where this is coming from, then certainly I think looking at where the carbonate signal is coming from, that would be a really good place to start looking or to consider and factor in. So I guess if you also looked at which so I'm pretty sure it's mostly biogenic rather than orthogenic carbonate here, but that still leaves you with your forams and your coccoliths, and that's something we, based on the XRF data, can't tell, but certainly would be really interesting to look at some smear sides or some assemblages to work out where this is coming from, because that must factor into this as well, for sure. Thanks for the questions. I'm looking forward to seeing the research. So hopefully that can spark some ideas on what to potentially work on in the future, as well as for what other, I'm hearing a lot of PhD projects for the future. So hopefully that can motivate some to apply. Lots to still explore.
Absolutely. And thank you so much for your presentation. And thank you everyone for joining in today. So we want to thank Anna Joy for presenting on SEDS Online. And thanks to everyone for attending for this week's seminar. Anywhere from, we've had those from China and Wales and Germany, as well as the United States. So thank you so much. Next week's seminar is at a regular time at 4 p.m. for the UK, when Hema Cassidy will be presenting on an alternative post-PhD career for academic publishing. The full abstract is on the SEDS Online website, and you don't need to register again for future seminars. You just use this same link, and we hope to see you all there. So thank you so much, Anna Joy, and we appreciate you coming by and giving your talk.
Oh, thank you very much for the invitation. It was really good fun. Thanks.
Absolutely. Thanks, everyone.